Good afternoon. I was about to wait a couple of minutes more for more people, but I think it will not work. So now we are going to start. So welcome everyone to the session Network Virtualization. As probably we are aware of that, IT virtualization is quite advanced comparing to network virtualization itself. So I think with this session we are going to prove that the network virtualization is also an advanced technology and it's capable of offering services to cloud infrastructures and to customers of network services. The first speaker in the session, Gino Carozzo, is an R&D project manager at Nextworks, an Italian SME that operates in the IT and telecommunications sector with major focus on control and management plane technologies. He will be talking on the cloud to network interface in the Bonfire infrastructure.
Thank you, Bartek. Good afternoon, everybody. So, in this brief talk, I will try to say a few words on our activities, research activities in the Bonfire project, which is an Internet of Service FIRE project, in which we are trying to look at the network from the cloud layer to some extent. So, what is the rationale behind a cloud-to-network work and research? Basically, network is the vital commodity for the cloud. No cloud exists without any performing network. And what we observe is that applications would like to have dynamic and flexible allocation of network plus IT resources. And control should be homogeneous and integrated among the two layers. But the state of the art is that network is basically treated as an always-on service, which means a static pipe basically established with a long-term existence, and in general, the application layer is unable to exploit all the automatic control potentialities of the networks. And the two dynamics of the IT layer with their workflows, their service procedures, is completely uncorrelated from the network ones. And there's a common trend that many presentations also showed before in other sessions to over-provision the network services when a cloud service or a cloud system needs to be integrated with in a dispersed and geographically distributed environment. In the Bonfire project, we have been looking at some reference network control technologies, and we tried to distinguish cloud or user-to-network interfaces from network control tools and suites that support them. And we further distinguished through this table, basically, academic solutions or solutions for the research and education networks from commercial solutions, which are also state-of-the-art and well-established in the market and in operational networks. And focusing on the first column, we highlighted the major items that for a project like Bonfire, which aims at production service, seems to be the more stable solutions for that sort of community, the community of the FIRE framework. And for the network control tools, we focused basically on the giant bandwidth on-demand system. And in terms of pure interfaces for a cloud layer to interface to the network layer, we focus on the Autobahn user access point interface with an eye open on the OGF NSI, which has been mentioned many times in this conference, and which is maybe the next step for bandwidth on-demand interfaces. I will neglect the contents of the second column. Many of you maybe just know them and are well experienced on that. So we have many solutions, but for a target community of research and education networks, maybe these are the more open and ready-to-use solutions for straightforward integration. A few words about the need of the cloud-to-network interface in a specific project like Bonfire. Bonfire is a cloud infrastructure in the FIRE framework for the Internet of Service community. And it tries also to go a little bit beyond the Internet of Service community, trying to integrate heterogeneous cloud resources, even from third-party cloud providers. Actually, and we have 6 test beds distributed across Europe, in Edinburgh, Bristol, in Ria Rennes, Stuttgart, IBBT, and Poznan. And these 6 test beds host permanent and on-demand IT resources, with permanent resources ranging around 300 of cores and 30 terabytes of storage, and the possibility to scale up with on-demand cloud resources up to 3K cores. And the key features of this project and infrastructure are the use of a seamlessly accessible access to the experiment, and an OCCI-based API to describe the experiment and interact with the infrastructure. And one of the key features, or the other key features of the project, is the possibility to contextualize the IT resources, the virtual machines that are allocated for a specific experiment, to the application that is going to run on that specific experiment. So in the end, the virtual machine comes up with some pre-configurations. And there is also the possibility to make elasticity experiments with on-demand resources and mechanisms to grow up and go down with the number of resources used for the experiment. This is another snapshot of the available resources, where you can see basically that 4 out of 6 of the Bonfire testbeds host on-demand resources and are capable of on-demand resources. Currently, the Bonfire infrastructure has a static network connectivity between all the 6 sites using the public internet. And this solution is basically wrapped by a middleware layer whose high-level architecture, very simplified, is shown in this slide, where basically we have a portal exposed to the user and a broker elaborating all the negotiation and brokering actions behind the experiment description. And then interfaces towards the different cloud providers, which are the different sites hosting the different Open Nebula instances or sales instances that are part of the testbed. Key important feature of this project is the existence of 3 specific usage scenarios. The first one is for cloud-only experiments, just allocation of virtual resources. The second one is cloud with emulated network, in which basically the existence of the virtual wall, which is a facility in IBBT, is used to emulate network behaviors like delays, jitters, affecting specific applications. And there are applications and researchers interested in using such an infrastructure. The focus of our research on cloud-to-network interface is in the third scenario, which is the extended cloud with complex physical network implications, in which the different sites are interconnected through GÉANT, and there is also the possibility to interconnect the different sites with other virtual resources provided by the Federica project in collaboration with the Novi project. And in the table below in this slide, you can see the different enrents we are talking with for the different sites in order to evaluate the possibility for a dynamic bandwidth on demand interfacing from the cloud layer to the network layer. And why do we need this? Because we have experiments and experimenters who want to test network-aware applications and that have specific requirements for guarantees in terms of bandwidth, QoS control, advanced reservations. And the solutions that we have been evaluating were mostly focusing on the GÉANT bandwidth on demand system, because basically all of our partners hosting the sites are in the research and education realm, and so they get better access to the network through their NRAN, and those NRANs also provide bandwidth on demand. And we choose Giant bandwidth on demand also because it appears now the most mature solution in terms of specification, implementation, and deployment in the beta testing that has been announced here in this conference, because it also provides on-demand and advanced reservations, and basically because Bonfire as a Fire project can benefit of the trial phase that is now going to be launched on the Giant bandwidth on demand product. And we studied a couple of use cases for this cloud-to-network work. One use case is, I would say, the more short-term focused, which is the usage of a shared site-to-site bandwidth on demand, in which we establish a pipe between two sites with specific quality of service, and we allow different experiments, the different dotted lines between the two Bonfire sites, to share the same pipe. There's a planning problem behind, obviously, the dimension of this pipe, but there are advantages in terms of costs, in terms of number of interactions between the cloud and the network. And this could be seen as a sort of first step towards the automation of the network and cloud interactions. Obviously, as emerged also in other sessions of this conference, there's a problem in the last mile. We need to configure the last mile in order to use the bandwidth on demand pipe established through Giant. And in a second use case, we have the same issue of the last mile, but we provide pipes per experiment. In this case, each experimenter declaring its experiment and requiring a certain number of resources, IT resources, CPU and storage, in different sites of the Bonfire cloud, will also declare the need for a specific connectivity between these IT resources. And these resources will be only owned and used in the context of that experiment. This is the much more dynamic scenario in which bandwidth on demand is used. So we expect much more interactions between our cloud middleware and the Autobahn system in this case. And this could be a good performance assessment for the Giant bandwidth on demand, as experiments may be many and with short term in execution, and the bandwidth on demand system can be solicited with many requests and along a day. Where we attach, on the bottom of this slide, you can see the very well-known Autobahn high-level architecture, and our work and our idea now is to attach to the user access point interface in a way to act as the web GUI of the Autobahn system. And this seems to be the more straightforward approach to interact between the cloud layer and the network layer. But obviously, the story is much longer in the sense that this UAP interface is basically located here where the pointer is, but we need to implement the business logic for managing this network service in all the middleware layers that we have in Bonfire in order to put a business logic for this new entity, the site link, the pipe between two sites, either in the resource manager or in the experiment manager or in the portal in order to expose information to establish this service to the user. And in terms of activities, functions that needs to be implemented, what we have is for sure, the basic tasks that we need to include for an interaction with the Autobahn, so the provisioning task for the request of bandwidth on-demand service reservations and the monitoring of the service status once it is established, but also in a new entity that we will include into our middleware, the bandwidth on-demand adapter. Also, we need to fulfill the need to implement the last mile, to configure the last mile. And for this task, we need to interact with the CPE, which is the front end for at least the CPE, which is the front end of the bonfire site, and for which specific configurations for the traffic presentation from the LAN side to the bandwidth on-demand pipe need to be established. A timeline for this to be in production. For the time being, all the design and the early prototyping phase has been completed, and we plan that by end of August, we will release the final specification of our work, the modifications to the architecture, plus the first prototype integrated into the bonfire infrastructure, so available for usage by different experimenters in the production. During September, we will have the early deployment of this. 2 sites for the time being, EPCC, which is Edinburgh University, the supercomputing center there, and PSNC, a testbed there in the PSNC premises. And for the time being, we are working basically on the use case number 2 in order to provide the users with the more longer-term spanning solution. And one key issue is that we configure as bonfire as users of the GÉANT bandwidth on-demand system based on the Autobahn interface, but we have also our users or customers to some extent, which are the experimenters who want to make their experiments to allocate these resources, network plus IT resources. And there are applications for this, and we selected this application through a mechanism of the open call, which is part of the FIRE projects. And the second open call of the bonfire project has been recently closed. There are evaluations in progress. I will give you some figures in the next slide for this, showing that there is interest for this sort of experiment. There is a community of researchers who is interested in playing with network and IT. And this project is the first project who tries to mix the two communities, the networking community and the Internet of Service community, to provide enhanced services for these users. And once the early deployment will allow us to assess and validate our production environment, we will move to the consolidated prototype. So end of the year, we expect final prototype fully integrated and operational, and full deployment, possibly extended to other bonfire sites in 2013. And the issue for extending the solution to other bonfire sites is basically related to availability of bandwidth on demand facilities and point of presence into the respective NRANs in Belgium, in France, in Germany. For the time being, those NRANs are not part of the pilot, so they are not part of our early deployment. But it could be the case that during next year, things will change. Interest from the users, bonfire users, towards network plus IT. We recently closed our second open call. We had a lot of oversubscription with respect to the available funding. We had 2 scenarios, 2 calls, basically, 2 topics on call. One was for experiments, so applications and researchers attaching to our infrastructure for testing scenarios 1, 2, or 3. And the possibility to include also a third-party cloud provider for a complete multi-cloud infrastructure. We received 28 project proposals, 7 of which are in the short list, and 4 of them mention scenario 3 as of high interest for their research. The evaluation process is still ongoing. Soon there will be the announcement of the new partners, but you can see that more than 50% of the proposal match this, this topic, this interest area. And they are going to start on September this year, so it's something to happen in a few months from now. And a further next step is the possibility to go beyond bandwidth on demand and to mix virtualized network resources with virtual or logical links that can be implemented through a bandwidth on demand system. And the idea is to mix bandwidth on demand from Giant with Federica resources and try to make, to provide the users of Bonfire with more complex experiment scenarios for this. And it's a nice to have, obviously. We are working now in parallel for virtualized network with Federica in Bonfire and bandwidth on demand. Sooner or later, we will come up with a convergence of the two research efforts and try to provide a single integrated solution. And that's it.
Thank you very much, Gino, for your talk. Are there any questions from the audience to the speaker? Well, I do have one. On what kind of problems have you find during this the design of the system as a whole? How you are going to use the two test beds? One of them is PSNC, I represent. The other one is EPCC. You mentioned that it's mainly due to the lack of autobahn deployments. Are there any chances to get other partners involved in experiments? This is critical.
I would split basically the issues in two areas. The last mile and the one side. In the one side, you are right. One issue is the bandwidth on demand service availability in the different NRANs. It could be nice to have all of the NRANs with those sort of services sooner or later. And concerning the last mile, if I should prioritize them, it's the much more important thing to solve, in the sense that as a production environment, it's quite simple to set up IT resources into a lab. The issue is, and the thing that make us struggling basically is how to connect these resources to the external network. And what we have is different departments in the universities, for example, for the IT and for the experimentation, and difficulties in exchanging information, difficulties in allowing dynamic control of IT and network resources of the department by a middleware like the Bonfire one. So basically, two areas of issues. The last mile is very, very important, so maybe we may need to work a little bit more there.
Okay, thank you very much, Gino, for your talk. I believe your feedback to Giant community will be really important. You are a big tester of the service Giant is deploying now. Thank you very much. The next speaker is Joan Antoni Garcia Espin. He's a researcher, project manager at the Distributed Applications Network area of the ITCAT Food Foundation, Barcelona, Spain. He's currently leading the Work Package 3 in the European FP7 project GAZES for the infrastructure virtualization.
Bartek. Okay, so good afternoon, everybody. Most probably, most of you, it's the second time you see me explaining. This is my official talk now, so I will not introduce myself again, because Bartek already did. Okay. So my talk today will be about the work we are developing in the Work Package 3 in the Gases project regarding infrastructure virtualization. We are doing a special emphasis in the network virtualization and how to integrate it into the existing solutions for IT virtualization. So what I will explain to you is the concept we have taken as a normal definition for virtual infrastructure in the Gases project, which is compatible with the ideas regarding this issue presented in previous European projects like Forward project, and also it's been discussed in the Jan community, in Novi project. So it's a quite common understanding, overall abstract understanding of what virtual infrastructure is. I will then explain you how we in the Gases project have designed and built what we call the logical infrastructure composition layer, which is nothing else than a thin middleware that provides the tools for managing together virtualization tools for IT and existing virtualization tools for network, or even creating our own virtualization driver for legacy boxes. After that, I will give some hints on the virtualization, the mapping algorithm we have published already in the academic side of the project for basically batching virtual infrastructure requests into the infrastructure and the performance of the model. And after that, some conclusions. So a bit of overview of the Gases project. Gases is a project composed for more than 14, 15 entities, partners, which are divided in research, industry, and academia. The coordinator is Interroute in Italy, and I2CAT is performing the technical leadership. But as you can see, we have quite balanced amount of partners. As I said, it's a big project. It's an integrated project which was funded in the call for. It lasts for 36 months. We are now in our last month, so we plan to end the project officially in December this year, but we are requesting for a small extension just to be able to better demonstrate the results we are obtaining and having more involvement from interested parties in the tools we are providing or in the concepts we are providing. And the budget is roughly over 10 million, and we are roughly under 1,000 person months. So the key facts, I already gave a hint on that, but are provisioning the tools for composing these virtual infrastructures, again, in the two realms, IT, so server virtualization and network. Then create the necessary extensions on an existing network control plane based on GMPLS plus path computation element to work with the virtual entities we generate from the physical resources in the network. Also define the business roles and the stakeholders that we foresee in the future could work with this model, with the model we present, with the architecture we present, which they are currently mappable to existing stakeholders nowadays in the service providers and so on. But we do not realize at all, but because we are very often used to see these monolithic companies owning from the infrastructure up to the very end user service. And also, we claim to be an enabler for integrating dynamic optical network services into the workflows that have to support cloud computing. So the architecture for the Gases project, the overall architecture is, as you can see on the slide, in a bottom-up explanation, we have the physical infrastructure, which is the gray layer you see on the bottom of the slide. We perform the network plus IT virtualization, and we generate virtual infrastructures, which is the layer immediately on top, which we create basing on the logical infrastructure composition layer tool that I will present to you today. On top of that, the next violet layer is for the controllers of the control plane, control management plane, and the enhanced extensions we provide. So between these two layers, we have a set of new actions, let's say, or new workflows, which are mainly due to the automation of the service provisioning on the network service provisioning or infrastructure service provisioning on top of already serviced virtual infrastructure. And finally, on top of that, we offer the on-demand network plus IT services to what we call the service middleware layer, which is the blue layer on top. And after that, here you have service consumers and a chain of services up to the end users. So as I said, the next of the explanation I will leave today focuses on this LICL layer. Okay. Before going a bit more on that, I want to give you some hints on what we have called the RORA model, which stands for Resources, Ownership, Roles, and Actors. The idea here is, since we want to decouple the actual service provisioning, infrastructure service provisioning, from the infrastructure management and control using virtualization, we define a set of 4 roles which have a predefined ownership templates on top of the resources, which grant them the rights to do some actions or other. And these roles can be grouped, of course, because the role is an abstract construct, into actors. So we can have an actor having more than one role. So as you can see, again, I will explain in bottom up. The lower blue bubble is the physical infrastructure provider, which is a role, the one that owns the physical infrastructure mainly. So we find the physical network IT resources on its administrative domain. The physical infrastructure provider has the tools that we provide to generate abstract representation of these resources and offer them as service to the virtual infrastructure provider, which is the next bubble on top, the VIP. At the same time, the VIP runs also the tools we provide to construct the virtual infrastructures, which add more information to the actual representation of the infrastructure. They include like security, policy, topology, and scheduling information, basically, about the infrastructure. Then the next bubble on top, of course, at this stage, I haven't talked about operating the resources. It's only representing the resources and being able to create an abstract entity, the virtual infrastructure, that's all. But on top, we have the virtual infrastructure operator, which will be the one deploying the control management logic on these resources. Then the virtual infrastructure operator will finally export a unified IT plus network services interface that we already developed on the project to whatever the consumer is. This consumer is, of course, generic way to say application provider, cloud provider, whatever, but not typically the end consumer. So more graphically, this gray layer belongs to the physical infrastructure provider. So this is the actual hardware, pipes, routers, servers, all deployed. What we do with the LICL is generate the virtual, the abstract representation of the resources, and attached to each of the representation, we provide web service, REST web service to interacting with the resource. So we are removing the specific CLI or SMP interface for the resource, and we are offering a common a web service interface to the resource, to the virtual resource, of course, and we manage the complexity of specific interfaces to different resources. The same happens to the IT side. Okay, so in the IT, if we already have, for example, cloud management system controlling different servers, like we do in the project, we use OpenNebula. What we do is just provide a driver for controlling the virtual machine, using a different endpoint reference for management. So we are not interacting directly with the interface of OpenNebula, but we export OCCI-like interface for doing that, so that we can remove OpenNebula, just deploy another systems like OpenStack, and we keep the functionality of the system. So these green virtual resources can be grouped in a virtual infrastructure using a set of tools, which is the domain of the virtual infrastructure provider. But as I said before, we need to include the control and management logic, which will be deployed by the virtual infrastructure operator. This means that, as you can see on the picture, we departed initially from two different gray layers, so two different physical infrastructure providers, and at this stage we have single green layer virtual infrastructure, which is controlled by a single management control system. Okay. What we have done here is just implement the extensions on the network control plane in order to be able to share information about the IT resources on the borders, and in this case, be able to provision IT-aware network services. And finally, of course, we export an interface for whatever the requester client management is on the application provider side to request these services. And this, in this case, I name it service provider. Okay, so about the virtual infrastructure. In the Geysers project, the virtual infrastructure is a collection of virtual network and IT resources before, which are abstracted from the physical infrastructure using RDF. And we have created a framework for that called the Information Modeling Framework, which we believe is flexible enough to be extended to model any kind of resources you may have on the infrastructure. A proof of that is that we have had collaboration with both the Novi project and Jam project in order to adapt this IMF to their needs for description of the infrastructures. So also the virtual infrastructure concept is very useful for us to include the infrastructure provisioning in the service workflows of the cloud computing or the application providers chain of services. Okay, and the key for that is that our LICL separates the specification of the capability and the attribute, so the infrastructure modeling itself from the implementation and deployment. Okay, on the right side you can see a very simplistic representation of what the virtual infrastructure description is. So we have four main parts, which are composed of general attributes, topology description, specific resource description, and then scheduling attributes. Of course, in the general attributes, we have, apart from identifier and so on, we have the security, all the information required for the security and SLA monitoring. So the way to manage the SLI is to define a very simple set of operations at the using the style of the cloud workflows based on creation, configuration, and decommission of the individual virtual resources inside the virtual infrastructure. So the major problems we had to face there are, first of all, the parameterization of the virtual resources, so creating the abstract model of each of the resources in the infrastructure, which can be standalone boxes, so modeling AeroIDM, for example, or can be modeling a whole ring of AeroIDMs, which is controlled by a single management system using an MTOSI interface. And on the other hand, we have the allocation of over the physical resources, which is actually the problem of, it's a well-known problem also from the past, of embedding the infrastructure into the virtual infrastructure into the physical infrastructure. In the picture, you can see a very simple schema, a status diagram of the different status of the different states, sorry, of the virtual infrastructure. But of course, I recommend you to check our documents in www.geysers.eu for further details on that. So one thing we are obtaining, one positive thing we are obtaining of this automated way of representing the infrastructure and offering interfaces for managing that, is that we are able to squeeze the provisioning timescales up to, well, you can see on the lower part, the current status for network planning, we can take months at the moment since we issue the request up to we get the whole bunch of devices installed, access, security, and so on, to from months to minutes in the case of using the automated tool for provisioning that. And also at the same time, we can provision the services in a even lower timescale. Okay, so in current status, it should take for us months to get the infrastructure and having the services deployed, especially if we are not the ones going there, plugging things and switching things on, configuring and so on. And now we can reduce it to a more machine-oriented scale in between milliseconds and hours, let's say. Okay, so about the logical infrastructure composition layer, I will be brief. I will only show you 2 slides because I think that it's worth to check the documentation for further details, and it will take me too long to explain all the design and the details of the implementation we have so far. So the LICL, the logical infrastructure composition layer, is split in 2 parts. The lower part, which is mainly for resource virtualization, so connecting to resources, getting the required information, creating the models, and registering to the future users, the virtual infrastructure providers. And the upper part, which is the one used by the virtual infrastructure providers this time, to grab the resources they can find on the different physical infrastructure providers they have, and implement the logic for putting virtual resources together and defining the virtual infrastructure and start offering this as a service to the infrastructure operators. Then all the communication, so the different interfaces we have implemented in the LICL is based on web services, mainly implementations made in REST, just as I said at the beginning, to be more in the flavor of cloud computing workflows. And the third main hot topic is that we use the information modeling framework for creating that. Okay, so this is a more detailed view of the functional architecture, but it's still very abstracted. As you can see, we have split atomic functions inside each of the upper and lower LICL, which are repeated because we took the decision of including overhead instead of having a system which could grow up in complexity, allowing different cross interaction between the different roles. So as I presented to you at the beginning, the roles have always to communicate each other one-to-one from physical infrastructure provider up to virtual infrastructure operator. And this requires a set of interfaces between them. So we don't allow, for example, a virtual infrastructure operator communicating directly with a physical infrastructure provider for a problem in the network provisioning, for example. So in the lower part, we have, of course, security. We have the control and management functions, as I said, to connect to the different resources, create the models, and grab the required information. We also have the virtual resource service management, so all the logic which is related to being capable of offering the resources we have registered from the physical infrastructure to the virtual infrastructure provider. Also, we have all the services for publishing this information and for managing the life cycle of the virtual resources and the SLA. And on the other part, more or less, we have the same structure, but this time we get rid of the complexity of the drivers of the different infrastructure resources. So I will go into the details of the model. What we publish here in Terena is the two-step solution we had for being able to optimize the way we deploy virtual infrastructures on the physical layer. First of all, we do some clustering of the infrastructure requests in order to maximize the utilization of the physical substrate. And after that, we implement an algorithm for mapping this into the physical infrastructure. So on the left-hand side, we have the virtual network requests, which are of different shape, of course, with different requirements, different time requirements, and we cluster them so that we can deploy several of them using same resources. So we increase the utilization of the physical resources that are in common, of course, without interfering each other. And then after that, we map to the physical topology. So given these network topologies, the set of network resources and network topology that we got, and a specified description of the physical infrastructure as a traffic matrix, and also the number of isolated networks we have to embed into the physical infrastructure, we try to find the optimal composition of this request to be mapped, and after that, map to the physical subset. So we have to find a trade-off between resource utilization and also control plane scalability. Why this? Because we may increase a lot the amount of messages exchanged in the different concurrent control planes of the physical infrastructure if we do not take care on that. So some results we included in the paper they are based mainly on comparing a random clustering of the virtual networks and mapping afterwards in the physical infrastructure to a logic based on integral linear programming to cluster them and then mapping that. So as you can see on the left-hand picture, the total number of wavelengths is on the vertical axis compared to the number of clusters on the horizontal axis. And the three lower lines in the graph show us that the maximum utilization of the substrate, the algorithm we have defined, is better, is not as greedy as the random collocation of the virtual network topologies, the virtual infrastructures into the substrate. And on the other side, we have, on the right-hand side, we have the effectiveness of this algorithm to map these virtual network requests into the physical substrate. So at this time, we see that the lines with the field icons on the upper part are representing the maximum utilization of the algorithm and are doing a better use of the capacity of the total capacity of the infrastructure compared to the random mapping. So what we have experienced with our 2.5 years of developing the project is that network resource provisioning can be and has to be integrated into cloud service provisioning workflows, and we propose a solution for that. The Geyser's holistic architecture helps on handling this converged INT and network resource service integration through virtualization and making a special emphasis on using the semantic description of the infrastructure for incorporating virtual network topologies into the workflows. So we also define, as I commented to you at the beginning, the RORA model for decoupling the different actions the different stakeholders can do on the infrastructure. And then we define the LICL, which is the element that helps us to perform these different actions. Also the IMF, as I commented, which is proven to help us on doing the semantic description of the infrastructure and then being able to offer these infrastructures as services, but not only the infrastructure, but also the individual virtual resources as services. And that the clustering of the VA requests, so the batching mechanism we propose shows an improvement of nearly 10% of the usage of the optical network resources in the embedding. So I take the chance to invite you to the next LICL demonstration. We will be done in the Future Network Mobile Summit in Berlin this July, sorry, and that's pretty much all. Thank you.
Any questions from the audience to the speaker? Victor. Excuse me?
Yeah, my question is, could you please tell to the audience which equipments are currently supported by this LICL in order to, let's say, have an idea of sort of hardware that can be virtualized?
Right, good question, yeah. So we are currently supporting both LSC and FSC equipment, and especially we have drivers implemented for Calian boxes. We also have for W1CIS, which is a Spanish manufacturer, and we have also for the ADBA boxes, ADBA R7, if I'm not wrong. In the IT side, we are currently able to control only OpenNebula managed servers, but we are working on extending this to more OpenStack flavor on that.
Any other questions? I do have one for you. Now having the hat of the NREN representative here, forgetting about my involvement in the project as well. Could you please say in few words, what is the message to NRENs from the Gazes project? What is the selling message? What we can offer as a Gazes project to the NREN community?
Yeah, in that case, I'm happy to say that we are already collaborating with the NRENs, especially with HEANet, on applying the model we have for decoupling the infrastructure services from the infrastructure management to what we call virtualized operation support systems. Okay, so we are trying to generate a virtual representation of the management, which splits the atomic functions, FCAPS, for example, the legacy one, and allows exporting the rights for managing each of these functions to different stakeholders. For example, in this case, in a simple experiment, the experimenter and the NREN. So a very simple service provisioning paradigm. We are working, this is work in progress right now, and we hope to publish something in the near future about that.
Okay. Thank you very much then.
Okay,
thank you. And the last speaker in this session is Ignace Bagdonas, Cisco UK. He's a solution architect at Cisco, working in advanced services team, focusing on service provider and data center network aspects worldwide. He's dealing with architectures and design of large-scale SP and data center networks, with particular interest in networking of the two. So, the floor is yours.
Okay, thank you, Bartek. Good afternoon, everyone, and thanks for your time for coming here. I do realize that I'm the last one in the session, and that means I'm the last obstacle between you and the dinner. So this way I'll try to be quick and light. it's a discussion about the topic of merging two separate worlds, at least worlds which used to be up to now. The data center, which is mostly the application part of the solution, and the network, which is considered to be a pipe and quite far away from applications. Now, seeing into the developments happening both in the industry and in the deployments and in the research, and standards development, there is a lot of activity happening here driven by the demand that data center networking needs to expand. And that expansion goes at really rapid pace, both in the absolute number of entities in a data center, increase of the bandwidth, increase of the requirements for that, mobility, geographical dispersion, and similar things. So, to set the context of this, two major players, the application and the network, both of them rely one on the other. If we are looking at them as a separate entities, that probably doesn't make too much sense. And talking about the scalability of something, and in general about the scalability, we need to set certain scaling limits. First thing, scalability is a broad topic. It means a lot for different people, it means a lot for different deployment models, and we certainly are talking about a different level of solutions if we have 10 network nodes, if we have 10,000 network nodes, and if we have 10 million network nodes. From the technology point of view, a lot of what is discussed here is still in the architectural development phase, or at the thought phase. It is thinking that what we can reuse, what we can develop, what we can well, reinvent or invent from the beginning in order to achieve the current requirements in the scaling. It's interworking of multiple standards development organizations. From a networking point of view, that's mostly ITF. There's also Open Networking Forum working in a similar area. Distributed Management Task Force from mostly from the application and from a virtualization, application virtualization point of view. So let's try to quickly set the kind of a reference model of what we are analyzing here. So a data center from a very high above. A few major components, major players, and here looking into this illustrative diagram, one thought which comes to mind if you, for example, look into adjacent area of service provider networks, have we actually seen this somewhere? Does it resemble, does this layering or the function separation and the connection of functions, is it actually what is being deployed in other types of networks? And certainly, let's look whether those scaling problems here might be similar. So basically, the players, we have the ancestor, the virtual machine. And further ahead, it is simply referred to as the host or the end node. The hypervisor, the element which sits between the actual VM and the rest of the network, and then two purely network functions, the top of rack element and end of row element, which sometimes is called the core component. And obviously we need another player, that is how do we get connectivity from outside of the data center into it. There's no bigger point of having a large setup without any ability to provide that service, which is boiling the inside. Scalability requirement is very simple. It has to be scalable and it has to work, period. Regardless of what we put there, regardless of current workloads, of current networking topology, of a lot of other factors, in the practical terms, it has to work. So there are multiple levels and multiple orthogonal planes from a scalability point of view, which have different scaling properties and which have different dimensions, which have different rate of change properties. So first is notion of identifier. The address, the tag, the label, some other form of identity which identifies something in the network. Most common ones are obviously addresses, layer 2, absolute majority of those setups use Ethernet, so the Ethernet addresses. Then we have at least a couple of source of IP addresses. Then we have the certain interworking function between the two. Then there's also a data plane component. So how do you separate logical entities which use the same physical infrastructure, the same physical piece of wire or some other network element? To abstract that from addressing point of view, that is one, but you also need to separate that from a data plane point of view, and that is a different namespace, that is a different region of identifiers, which might have completely different scaling properties. Very simple example. In IP namespace, in IPv4 namespace, we have 32 bits. Well, of course, we cannot use all of them, but if we look into Ethernet namespace for tagging, that's just 12 bits, and still we cannot use all of them. Trying to represent the logical components in the network which are needed for the scalability also increases the exact same amount of all those entities, like tunnels, logical interfaces, filters, and all those tiny details. The manageability aspect of that, the OAM, the operations, administrations and management part of the house, you also would be happy to have some ability to actually see what is happening in the network and to control it to an extent. Diagnostic functions, to an extent accountability functions, that also has specific scaling properties which tend to grow with the size of the DC network. There are multiple types and classes of different deployment models, but as a majority and probably the most wide deployment is a multi-tenant data center where we have multiple entities sharing the same physical infrastructure. That is also true for external connectivity. Therefore, we need to have some form of a solution which allows to have scalable and expandable connectivity outside, between the data centers, between a data center and some user cluster, between some other networking entity. So that is yet another layer or another sub-area which needs to be addressed. So starting from addressing and trying to look into some practical ways and approaches which could be used for that. So if we try to analyze, we have virtual machines in the network, in a data center. Virtual machine, as a rule, is not the entity which you can easily modify. That's typically a stock operating system, which, okay, it might be open source. That means that you need to go there deep and do something. So typically, this is not modifiable entity. Therefore, if you need to do something deep with the network, that is not the right place. Looking from the point of view of the external network connectivity, there's an edge gateway, the node which understands the network topology and knows the reachability properties of each and every virtual machine in a network. In simple terms, it has the binding between the IP layer and the underlying Ethernet layer. And that might not be a small number. Looking into the way how that is built, typically, or at least traditionally, that is built by using some helper protocols on IP and Ethernet interworking, and that is built from a data plane learning. The intermediate nodes, the end of row, and top of rack nodes, they build their forwarding state by looking into the data plane operation. That typically works. That is not necessarily the most deterministic and the most scalable approach. But if we look at one important property of the end hosts, they do have addresses. Those addresses are stable. And addresses are stable both on the IP layer and on the underlying layer 2, Ethernet layer. And the binding between the two, there's ARP neighbor discovery. Well, we are still a couple of weeks before the 6th of June, therefore we still have only ARP. Neighbor discovery will come later. The binding between the two is done by certain distributed lookup mechanism, and that's broadcast technically, which spans a lot of the network diameter. What if we do a rather radical approach? We simply remove ARP as a function. it doesn't exist anymore. Of course, we cannot remove it from the end host. We need to adapt, well, put something like an adaptation layer or a shim in the middle, which intercepts that outgoing ARP request. And for example, queries are centralized or distributed, queries out external directory or database or something like a mapping system, and gets back the response of whatever it wanted to learn. Whether it wanted to learn an address of a neighbor, whether it wanted to learn the layer 2 address of a gateway or something like that. Another possible option is looking into amount of bits in all those two layers. What if we do a rather simple but radical approach? We take IP address and simply stuff it into the last 4 bytes of the Ethernet address. Why not? Okay, not maybe the last 4 bytes, the ones which you like, but you define a one-to-one mapping function. And with this, the ARP as such is not needed anymore. Given that you have one of the addresses, you can derive the properties of the other ones. So, 2 possible options, not necessarily they are recommended in all the cases. Not necessarily they scale to extreme limits. Not necessarily they are fitable into all the deployments. But that is a general way of thinking, that we should stop relying on learning from a data plane. Given that the majority of data center provisionings are done centralized, so basically we have an orchestration function which has knowledge about all sorts of details, including physical location, network attachment points, addresses of all sorts of all the infrastructure in the network. That information is available. It's just a question of trying it and taking it and reformatting in the way which we need for building the sufficient forwarding information into the network. This leads to the definition of an entity called network controller. And here the topic comes close to open networking and network controllers in general and different forwarding paradigms. That is just one of the applicabilities of such type of solutions. Network controller has interface to all the network infrastructure. It can provision the forwarding state into each and every network element. The information needed for that network controller to do this is already available in the orchestration system or in some other source or entity which has information about an inventory of a data center. Therefore, we don't need learning from a data plane. Probably in this particular case, we also don't need control plane. It's just enough to push down the forwarding state into each and every intermediate network element. This has one interesting property of security. If there is no need for a node to have global reachability in a data center, we can very easily achieve that. Just provide the forwarding state into intermediate nodes in a way that there is a reachability only among the pairs or groups of the nodes which need to communicate together. However, this looks nice, but it starts to break very easily when we start talking about the mobility. And mobility here is meant by the migrations, the moving of the VMs from one point of place in the network to the other. From a point of mapping layer 2 to layer 3 addresses, that's not a problem, they stay the same. But what changes is a point in a point of attachment in the network. So the challenge to that is that the application level or virtual machine mobility is controlled by a different entity, that's application controller, which has understanding about the current load of VMs, resource usages, and similar things, and it can take one or other decision and move some VM from one place to the other. That is completely disconnected from a network. A network for that is just a pipe. So, from this perspective, there's no signaling between the VM and the network, and that is one of the requirements which is needed in this case. However, how does that scale? If each and every VM will start talking some control protocol to the network, to some entity in the network, probably we will run in another scaling bottleneck. What if network and application controllers start communicating together and start cooperating, in a sense that application controller, which understands the application level topology of a DC, says, right now I will need to move this particular entity to that particular place. Dear network controller, please do your part. Please provision the intermediate forwarding state, the final forwarding state into all affected network elements, and tell me when that is done. When that is done, I will take care of moving one VM to the one VM from one place to the other place. Looking further and trying to solve these problems, we hit up some fundamental aspects of routing scalability, or in general routing information state scalability. Certainly, we can have a type of solutions based on IP mobility, and that might work. So basically, we have some part of infrastructure denoted as a home agent, and it takes care of where the VM currently lives. But as mobile IP does not scale and has fundamental properties in this area, trying to apply that here also doesn't work. One of the practical approaches, and that's by definition not the only one, and that's not the absolute truth, that's just the current thinking, that one of the possible approaches here is to build another layer. A very simple computer-sized approach. You can always build another layer of indirection and solve the problem. Why not try doing that here? So we define the overlay, the network which has understanding or a representation of a networking topology which is important from a VM perspective, and which has completely isolated all the other aspects of that. So basically, we abstract the underlay, the underlying physical, or to some extent formal, to some extent logical infrastructure, and simply partition our data center from this perspective, that for a certain group of virtual machines or some other elements which need to communicate, we build the overlay, which is something like a closed user group, which provides the connectivity among all the interested elements here. As we have another layer, we need another layer of identifiers, of course, simply to identify the elements there, and that's a virtual network ID. What it is today, it's still not very clear. Well, there will be some data plane representation. There will be probably that many bits or maybe that many more bits. It's still work in progress. That is an identifier which identifies the VM in a context of a particular virtual network, and at the same time allows to identify the overlay network among the set of the underlays. This brings another interesting scaling problem in another area of a data center network. So if we have now separate addressing namespaces, if we have separate data plane representations, that means that all nodes in a DC need to be able to understand that, which we cannot assume. Again, due to the same reasons that we cannot change all the guest VMs, we probably cannot change and will have to live with incremental network elements, features, feature sets, and then similar things. We need to define another element, the gateway between the new world and the old world. So the function of that gateway is to translate between the overlay plus underlay construct into only the underlay construct if we need to have the connectivity between the two. And in fact, we need more than one such gateway, at least 3. It might be the case that we need to communicate between the VMs which are under the new world order and old world order in the same data center. It might be at the separate data centers which are across, where there is a certain separate interconnect mechanism between those two data centers. We also need to have ability still to reach the services into the data center. That means that the edge gateway also has to have reachability into the new world nodes connected to that. This brings in an interesting question of where to place this functionality. Can we do that in an actual virtual machine? No. Very unlikely. Can we do that in a hypervisor? Possibly. That's one of the possibilities. Can we do that in the top of rack element? Possibly. That's one of the other possibility too. The question is how much state is accumulated in each of these points, and how scalable it is from mobility perspective, how scalable it is from end-to-end application reachability perspective, what signaling is required from a host in order to query the topology, whether the host needs to query such topology, whether the host understands that everything is a flat network, or does it have some visibility into the network topology if, for example, we have applications like Anycast or something which relies on understanding of some routing information to the network. And this is just a quick, quick illustration of current thinking of where the overlays could be placed and how that could work together with various gateway functions. Topology. Given that we have some network and we have separate layers in that network, typically the overlay hides the topology of the underlay. In general, that is good, but not necessary in all the cases. It might be necessary, again, to inject some underlay topology, information visibility back into the overlay. Mostly for application-related reasons. It also might be needed for resource optimization and similar aspects. However, there comes another interesting scalability problem. Probably currently is the wrong word, but the general thinking in the data center networking area is that all sorts of multi-point forwardings, including multicast, broadcast, and flooding of unknown frames and similar multi-point constructs is not good. It just doesn't scale. And it doesn't scale even more if we have overlay. So if we have an overlay and we need to do multicast replication, well, several options. We need to rely on the underlay multicast forwarding capabilities. We need to do ingress replication. We need to build forwarding tree with replication points on the overlay, something similar. So this proves not to be practically scalable. Therefore, current thinking is that it is easier to adapt the application to avoid multi-point operation, multi-point connectivity, than to try to build the data center which allows for such application to operate without any changes. Again, there is no one single answer. And the solution is somewhere using certain parts of these components together to a certain rate. Dynamic control plane is required, but at the same time we have controllers, the controller entities. And both of these entities cannot operate completely blindly, standalone, and autonomous. They need to interwork. Dynamic control plane needs to have some visibility of what network controller is trying to put in a forwarding state, and for very simple things as not to overrun one onto the other. It's also about efficiency. To see the topology of a network from a distributed application point of view, it might be more complex and simply may require a significant more amount of time to come to that same conclusion, as the single network controller can do that centrally from a central point. This is a little bit of alphabet soup, just to give some brief overview into which directions these types of solutions are coming, not looking deep into these technologies, just separate logical groups. Whichever choice you prefer, pure layer 2, Ethernet-based solutions provide a backbone bridging, shortest path, trail, which is slightly basically same solution but coming from a slightly different angle. Including external connectivity between the data centers, EVPN, Lisp as another, probably extreme would be the right word here. Stateless transport tunneling. This is a rather creative but also extreme solution how to overcome all sorts of middle boxes in the in the network which we have here, and trying to do things which would otherwise break them in order to hide ourselves. And of course, MPLS family. It's not only MPLS, but MPLS family of solutions. And I do understand that certainly for somebody, words data center, MPLS, and BGP in the same sentence will increase blood pressure. That is a way of one of the ways of thinking. There's nothing wrong with BGP. BGP is a very simple and very scalable routing protocol, and it works happily today. Quite contrary, if you would like to put something like 5 million routes into your favorite ISIS or SPF. On another hand, MPLS in the data center, this is something probably radically different, but the question is, how data center network, purely from a network architecture perspective, is different than the service provider network. Putting aside that in the service provider network, the end user is, well, is the user. And in a data center network, the end user is the host. From a network point of view, there are not that many differences indeed. So this is just a possibility to pick and select and choose whichever you want, depending on what is currently deployed, what are the possibilities from a technical point of view, technical preferences, layer 7, 8, 9, and religion, and all sorts of other things. And also including how broken is that from an architectural point of view. From an operation point of view, each practical network is running. And each practical network needs to be supported somehow. It needs to be taken care of. It needs to be at least monitored and maintained. To scale it from the architecture point of view, to scale it from a data plane point of view, to scale it from a control plane point of view, that is one. But this also needs to be looked from a perspective of the operations. How scalable is OEM constructions here? How quickly the rate of state changes as we grow the network from an operations point of view. How many identifiers and to what flooding scope do we have? Do we have 5 million hosts and some global space of some identifiers? Do we have another extreme, a lot of point-to-point links, which have 2 identifiers, and all those 2 identifiers are the same across 2.5 million of communicating peers in your data center? If we're using something like a mapping system or central directory or some other lookup mechanism, how scalable is that? What happens if, for example, your network, imagine, gets under a spike of load or a denial of service or something like that, which requires a lot of topology lookups? How scalable is that from a mapping point of view? How scalable that is from a control plane perspective if there are topology changes within the network? Also, how the scalability aspects of security solution work here? Do we trade security aspects here for scalability? And how can that be still manageable, operational, and secure enough? Now, looking back into what we discussed here, the emerging trends in general are that we are going to the overlay model. An overlay model termination points tend to be in a hypervisor, or at least as close to a virtual machine as possible. That is to contain the state. The state of, again, here Lisp has a very nice architectural, and not only Lisp, LNP and all other identifier location splitting mechanisms, they have a very nice property that we have the same 32 bits which have different meanings. There's identifier and there's locator. There's probably no need for each and every pair of entities to completely understand where, in the sense of a network topology, the communicating pair is, as long as we have an identifier which uniquely identifies where that pair is. From a routing perspective, probably there's no need for each and every network entity to know where exactly each and particular endpoint, virtual machine, or end host is. As long as we can uniquely identify that that particular VM lives in that direction behind that top of rack or a hypervisor element. Scalability aspects of the first hop data plane. That's all about the space of identifiers. If we have Ethernet and we have Ethernet tags, maybe now 12 bits, which are only local scope between the point of attachment on the top of rack element and the point of attachment at the hypervisor element, that's significantly higher amount of bits which we can use compared to if those 12 bits had a global scope, or at least partially global scope across a portion of your data center network. The state required in the top of rack element. Two directions of growth here. It sees two sides of the network. One is the hosts and hypervisors and potentially visibility into the VM addressing layer. The other side is addressing towards the other top of rack or edge elements. It seems like there are 2 different address spaces. Yes, that is correct. But together, the amount of state in those 2 different address spaces is significantly lower than if we would have one single addressing space. For the gateway, pretty similar scalability aspects, with the exception that gateway likely does not have and does not need to have information about each and every endpoint. It is enough to know over which top of rack element each particular VM is located, and we can use as simple mechanisms as aggregation in order to contain the amount of state expansion. So as a summary, and that is an open question, adding another layer, of course it's fun, but does that solve a practical problem? And that's why the question mark over there. At least it seems that this way can lead somewhere. That is not going to be a quick and easy path, and that probably will be another 200 RFCs, by the way, by trying to achieve that, but it seems that that is eventually needed. Certainly we will see more and more practical deployments of controller elements, and controllers and dynamic control plane will have to interwork, and that is true for pretty much every emerging controller-based trends which we see currently in the network. And another important aspect to try to notice here is we have spent probably the last 15 years trying to scale service provider networks. And looking from a perspective into what data center networks are developing, that starts to resemble yet another form of service provider network. There is a lot of good research and good solutions developed for the SP segment. And maybe it makes a lot of sense to try, at least to analyze and try to reuse that. So with this, my presentation is over, and I would be happy to discuss questions, heretic thoughts, and any other call it pain points, which would especially be interesting for me to hear the pain points from you as an operator community. What do you see in your general data center networks? Whether this is an area which is painful for you, or maybe you already have a solution for that. Is it relevant? Is it something which is important? And thank you for your time then. With them.
Very simple question. Why we not hear from your presentation what clouds? If all people actually data center talking about resources virtualization for cloud and so on. So what's the
cloud is something which runs over the network.
No, you need still virtualize VM, you need to manage resources and provide internal infrastructure between a cluster, inside cluster, VMs.
Exactly. That's a different layer. So that is much closer to the application layer of a data center. But eventually, it comes down to the network. The cloud is just a representation of the state of the VMs, of certain aspects to accessing to it, manageability aspects, and a lot of other interesting things. It's not saying that that is not important, but eventually, the cloud is composed of network elements connected together over the network. So in order for cloud to work, the network has to work.
But still, we studied implementation of network and network for cloud, for data centers. We still saw the quite a few years ago Cisco papers and quite interesting papers from Alcatel-Lucent and from Juniper that they propose quite applicable a solution for intra data center ready for cloud, like any-to-any implementation matrix.
Okay, so 2 points here. One, this is what is here. Yes, I do represent a somewhat known vendor, but this is, call it vendor neutral, or at least vendor independent to an extent. This is more of an overview of the problem, one particular problem here. The second point is that this is not talking about a particular solutions. Yes, there were some acronyms, some possible names for that here, but that is not the essence. The essence is trying to understand the problem and trying to characterize the problem of scalability. Yes, you can say that, and of course, there are solutions which are deployable today. There are different size, different scale of the networks. I cannot recommend or even direct to any single solution which would be applicable for each and every case. And that is not the goal. The goal is not to talk about the solutions here. The goal is to talk about the certain properties or more the requirements for the solutions. There are solutions now. There will be other solutions upcoming. This is a dynamic field. And certainly we will see incoming new technologies or incoming new solutions. We certainly will see applicability of existing ones or tweaks of the existing solutions into these new deployments. But before that is being done, we need to understand the problem to have the requirements which need to be fulfilled by those solutions. So my talk here is about mostly about the requirements. What do we need to do in order to come there? It's not talking about the solutions. So I hope that at least clarifies the context.
So when talking more about networking in the data center, I keep worrying about how to connect the customers to their maybe private networks in the data center in respect of speed, so 10 gig or even faster, and how to separate these traffic from each others. So what is your opinion? Would you tend to extend the overlay to the customer or use some other things to connect?
Okay, so there are two parts here of this. One, the separation of the VM and resources which are allocated to that particular customer or entity within the data center. And then there is another part which is outside, basically the networking part. So overlay is the construct which is defined within the data center. Certainly it can be, from an architectural point of view, it's certainly possible to extend overlay into the customer's network. How practical is that? There might be cases where it is practical, but I would tend to believe that in majority cases this is not practical, for a very simple reason. If there is a service provider network which provides some form of separation for multiple customers or multiple entities here, the solution is already there. We just need to reuse it. Why invent something else? So in this case, and that was briefly touched about roles and functions of each of the network entities. We have an edge node, which has the view of both worlds. It has insight into the overlay topology, and it also has insight into external network connectivity. And in this case, we would need something like an interworking function. Okay, I would expect now that somebody from ATM days would throw a rotten tomato into me, interworking function. Something like a mechanism mapping from the separation element entities from service provider side, VPN ID, pseudo-VI ID, tag, anything else, into the identifier namespace of the overlay. So to answer in short, yes, it is possible to extend overlay externally, probably not practical. It is also possible to map the external and internal separation identifiers, and that is much more practical.
Okay, I think it's time to stop the discussion. Probably we can continue offline. Thank you very much for your presentation.